Welcome, curious minds, to a journey into the uncharted territories of human knowledge. We live in an age of unprecedented scientific advancement, where we've mapped the human genome, peered back to the dawn of the universe, and even glimpsed the elusive Higgs boson. Yet, for all our brilliance, the universe, and indeed our very existence, remains a tapestry woven with threads of profound mystery. Tonight, we embark on an exploration of 100 things science still can't explain. From the depths of our own minds to the farthest reaches of the cosmos, prepare to confront the limits of our understanding, and perhaps to feel a renewed sense of wonder at the vastness of the unknown. 1. Consciousness. The most profound mystery of all, perhaps, is consciousness itself. It's the very fabric of our subjective experience, the what it's like to be us. We can describe brain activity, map neural pathways, and even understand how sensory information is processed. But none of that explains why we have an inner world. Why isn't it all just electrochemical reactions? Why do we feel, perceive, and have a sense of self? Is it an emergent property of complex neural networks, a fundamental aspect of the universe, or something else entirely? Scientists can measure its correlates, the brain states associated with being conscious, but they cannot pinpoint its origin or mechanism. We don't know why some creatures appear to have it and others don't, or where the line is drawn. The hard problem of consciousness, as philosopher David Chalmers termed it, remains stubbornly unsolved. How do physical processes give rise to subjective experience? It's a question that challenges the very foundations of our understanding of reality and ourselves, a frontier where neuroscience, philosophy, and even quantum physics converge in their inability to provide a definitive answer. 2. Why we dream. Following closely on the heels of consciousness itself is the enigma of why we dream. For millennia, dreams have been attributed to divine messages, subconscious desires, or prophetic visions. Modern science has peeled back some layers, linking dreaming to specific brain states during REM sleep, but the ultimate purpose remains elusive. Are dreams merely neural garbage disposal, consolidating memories and flushing out irrelevant information? Do they serve as a safe space for the brain to simulate threats and practice problem solving without real-world consequences? Some theories suggest they are essential for emotional regulation, allowing us to process difficult experiences. Others propose they foster creativity, weaving together disparate ideas into novel connections. Yet none of these hypotheses fully explain the often bizarre, illogical, and intensely vivid narratives that unfold in our minds each night. Why do we experience such elaborate internal cinema, and what precise evolutionary advantage does it confer? The sleeping mind holds secrets that, despite decades of research, continue to defy a singular, universally accepted explanation. 3. Placebo effect. The placebo effect is a medical marvel that consistently baffles researchers. How can a sugar pill, a saline injection, or a sham surgery produce genuine physiological improvements in a patient's condition? It's not just about feeling better. Studies have shown measurable changes in brain chemistry, hormone levels, and even objective clinical outcomes for conditions ranging from pain to Parkinson's disease. The mind's ability to heal the body simply through belief and expectation is undeniably powerful, yet its exact mechanisms remain largely unknown. Is it purely psychological, tapping into the body's natural healing processes, or does it involve deeper, unquantified connections between our mental state and physical health? While we can observe its effects and even harness them in clinical trials, the precise pathways through which belief translates into biological change are still a profound mystery. Understanding the placebo effect fully could revolutionize medicine, but for now it stands as a testament to the inexplicable power of the human mind. 4. Near-death experiences. Near-death experiences, or NDEs, are perhaps one of the most compelling and controversial phenomena related to consciousness. Reported by individuals who have come close to death during cardiac arrest, severe trauma, or deep coma, these experiences often share striking similarities: out-of-body sensations, encounters with deceased loved ones, journeys through tunnels of light, and feelings of profound peace and unconditional love. While skeptics attribute NDEs to brain hypoxia, endorphin rushes, or psychological coping mechanisms, these explanations struggle to account for the vivid clarity, detailed memories, and often life-altering transformations reported by those who undergo them. How can a brain in the throes of collapse, often with no measurable electrical activity, produce such intricate and consistent narratives? The scientific community has yet to provide a comprehensive physiological explanation that fully reconciles these extraordinary subjective reports with our current understanding of brain function and the cessation of life. The question of whether consciousness can exist independently of the brain, even momentarily, remains a tantalizing and unresolved debate. 5. Déjà vu. That fleeting, unsettling sensation of having experienced something before, even when you know you haven't, is known as déjà vu. It's a common phenomenon affecting a significant portion of the population at some point in their lives, yet its precise neurological underpinnings are surprisingly difficult to pin down. Is it a glitch in memory processing, where a new experience is mistakenly tagged as an old one? Perhaps a momentary hiccup in the brain's temporal lobes, causing a slight delay between the perception of an event and its conscious recognition? Some theories suggest it's related to subtle shifts in attention, where a scene is briefly perceived subconsciously before being consciously registered, creating the illusion of a repeat. However, no single explanation fully accounts for its spontaneous nature, its variability, or the profound sense of familiarity it evokes. Despite its prevalence, déjà vu remains an elusive cognitive quirk, a momentary wrinkle in our perception of time and memory that science has yet to fully iron out. 6. Savant syndrome. Savant syndrome is a rare and extraordinary condition where individuals, often with developmental disorders like autism, exhibit incredible abilities far beyond the norm, typically in specific areas such as memory, mathematics, art, or music. Think of a person who can flawlessly recall entire books, perform complex calculations instantly, or reproduce intricate musical pieces after a single hearing. The puzzle lies in understanding how these islands of genius emerge in individuals who may otherwise face significant cognitive challenges. Is it a compensatory mechanism where other parts of the brain are underdeveloped, leading to enhanced function in specific areas? Does it involve unusual neural connectivity or atypical brain organization that allows for hyperfocus and exceptional processing in certain domains? While some research points to potential links with brain injury or specific genetic factors, the precise neurological pathways and developmental triggers that give rise to such astonishing, isolated talents remain largely unknown. Savant syndrome challenges our understanding of intelligence, disability, and the brain's untapped potential. 7. Autism origins. Autism spectrum disorder, or ASD, is a complex neurodevelopmental condition characterized by challenges in social interaction, communication, and repetitive behaviors. Despite decades of intensive research, the exact origins of autism remain largely a mystery. We know it's not caused by vaccines, and it's certainly not a single condition, but a spectrum with vast individual differences. What we do understand is that genetics play a significant role, with hundreds of genes implicated, but no single autism gene has been identified. Environmental factors are also believed to contribute, potentially interacting with genetic predispositions, but these triggers are still poorly understood and difficult to isolate. Is it an atypical pattern of brain development in utero, an imbalance of neurotransmitters, or a unique way the brain processes information? The sheer variability of autism makes it challenging to pinpoint a singular cause, leaving researchers with a multifaceted puzzle of genetic, environmental, and neurological factors that combine in ways we are still struggling to comprehend. 8. Alzheimer's root cause. Alzheimer's disease, the most common form of dementia, slowly and relentlessly erodes memory, thinking skills, and eventually the ability to carry out the simplest tasks. While we've identified hallmarks like amyloid plaques and tau tangles in the brain, the fundamental root cause of these destructive processes remains elusive. Are the plaques and tangles the cause of the disease, or merely symptoms of an underlying more fundamental problem? Is it a metabolic disorder of the brain, an infectious agent, a chronic inflammatory response, or perhaps a complex interplay of genetic predisposition and environmental factors? Despite billions of dollars in research and numerous drug trials, we still lack a definitive answer to what initiates this devastating neurodegenerative cascade. Without understanding the true root cause, developing effective treatments that prevent or reverse the disease remains an immense challenge. Alzheimer's is a ticking clock for millions, and its ultimate trigger continues to evade our grasp. 9. Aging mechanism. Aging is a universal biological process, an inevitable journey for all complex life forms. Yet its fundamental mechanism remains one of biology's greatest unsolved puzzles. Why do our bodies deteriorate over time? Is there a master aging gene or a specific cellular program that dictates our lifespan? Current theories range from the accumulation of cellular damage, like DNA mutations and telomere shortening, to programmed senescence, where cells stop dividing, and even the idea that aging is a trade-off for early life reproductive success. But none of these fully explain the entire complex phenomenon. Why do some species live for mere days, while others, like the Greenland shark, can exceed 500 years? What initiates the decline in cellular repair mechanisms, the weakening of the immune system, and the overall physiological breakdown? Understanding the precise molecular and cellular mechanisms of aging could unlock profound secrets about human health and longevity, offering the potential to not just extend life, but truly enhance its quality in later years. 10. Why we sleep. We spend roughly a third of our lives asleep, a state of reduced consciousness and physical activity that on the surface seems incredibly vulnerable and inefficient from an evolutionary perspective. So, why do we sleep? While we know that sleep is vital for survival, severe sleep deprivation can be fatal, the precise overarching reason remains a subject of intense scientific debate. Is it purely for energy conservation, a time for the body to rest and repair? Or is its primary function neurological, allowing the brain to consolidate memories, clear metabolic waste products like amyloid beta, and reorganize neural connections? Some theories propose it's crucial for emotional regulation and processing, or even for bolstering immune function. However, no single theory fully encompasses the vast array of physiological and cognitive changes that occur during sleep, nor does it explain why different species require such wildly varying amounts of rest. The necessity of sleep is undeniable, but its fundamental purpose continues to be an enigma tucked away in the deepest corners of our minds. 11. Animal migration precision. From the smallest insects to the largest whales, countless animal species undertake astonishing, epic migrations, often spanning thousands of miles across continents and oceans. The sheer precision of these journeys is what truly baffles scientists. How do monarch butterflies, with their tiny brains, navigate from Canada to Mexico, a journey that takes multiple generations, with offspring returning to the exact same forests their great-grandparents left. How do sea turtles find their way back to the precise beaches where they were born, decades earlier, to lay their own eggs? While we've identified some navigational tools, like the Earth's magnetic field, the sun's position, and olfactory cues, these don't fully explain the incredible accuracy, the innate knowledge, or the complex multimodal integration of information required for such feats. The mechanisms underlying this innate GPS system, passed down through generations, remain one of the most magnificent and elusive mysteries of the natural world. 12. Homing pigeon navigation. Homing pigeons are legendary for their uncanny ability to find their way back to their lofts from hundreds, even thousands of miles away, often through unfamiliar territory. While we know they utilize a combination of cues, the Earth's magnetic field, the sun's position, landmarks, and even infrasound, the precise way they integrate these diverse sources of information into a reliable internal compass and map system is still not fully understood. How do they create and store a mental map of their surroundings, and how do they recalibrate it on the fly? Some research suggests they might even detect subtle olfactory cues or variations in gravity. However, the exact neurological mechanisms that allow their brains to process and prioritize these inputs, especially in varying conditions like cloudy skies or unfamiliar release points, remain a subject of intense research. The humble homing pigeon holds secrets to navigation that continue to challenge our understanding of animal cognition and sensory perception. 13. Bee communication complexity. The intricate social structure and cooperative behavior of honeybees are utterly fascinating, but their waggle dance communication system remains a marvel that science is still trying to fully decipher. When a scout bee discovers a new food source, it returns to the hive and performs a precise dance that conveys the direction, distance, and even quality of the food to its hive mates. How do other bees accurately interpret these complex movements, angles, and durations to locate the exact nectar source, sometimes miles away? While we understand the basic principles, the nuances of the dance, including how bees account for wind, terrain, and even the sun's changing position, are still being unraveled. Furthermore, the genetic underpinnings of this sophisticated language and how it evolved to such a high degree of precision are also largely unknown. The waggle dance is more than just a simple signal. It's a sophisticated form of symbolic communication whose full depth and origin continue to mystify entomologists. 14. Cat purring mechanism. The gentle rumble of a purring cat is a sound of contentment and calm, but the exact physiological mechanism behind this unique vocalization is surprisingly complex and not fully understood. Unlike other vocalizations, a cat's purr is produced during both inhalation and exhalation, creating a continuous sound. It's thought to involve a rhythmic contraction and relaxation of the muscles of the larynx and diaphragm, leading to a rapid vibration of the vocal cords. However, the precise neural control system that orchestrates this continuous, low-frequency sound and how it differs from other forms of vocalization is still debated. Furthermore, while we associate purring with pleasure, cats also purr when they are stressed, injured, or even giving birth. This suggests the purr might serve a dual purpose, not just communication, but also a self-soothing or even healing mechanism, as the low-frequency vibrations have been linked to bone growth and pain relief. The simple purr, it seems, holds deeper secrets than its soothing sound suggests. 15. Whale strandings. The heartbreaking phenomenon of mass whale strandings, where dozens or even hundreds of whales beach themselves and often perish, remains one of the ocean's most enduring and perplexing mysteries. While some individual strandings can be attributed to injury, illness, or old age, the large-scale events, often involving healthy animals, defy easy explanation. Theories abound. Naval sonar disrupting their navigation, seismic surveys, sudden changes in underwater topography, extreme weather, or even errors in their magnetic compass system.
However, no single theory consistently explains all events, and often multiple factors could be at play. Why do these highly intelligent social animals collectively make what appears to be a fatal navigational error, often in seemingly clear conditions? The vastness of the ocean and the difficulty of studying these events in real time make it incredibly challenging, leaving us to wonder about the silent distress signals that lead these majestic creatures to their untimely end. 16. Octopus intelligence. Octopuses are invertebrates, lacking the complex brain structures typically associated with advanced intelligence in vertebrates, yet they display astonishing cognitive abilities. They can solve complex puzzles, use tools, navigate mazes, remember solutions, and even escape from seemingly secure enclosures. Their intelligence seems to have evolved entirely independently from our own, making it a truly alien form of cognition. The mystery lies in how their decentralized nervous system, with 2/3 of their neurons located in their arms, gives rise to such sophisticated behavior. How do their arms, which can act semi-autonomously, coordinate to achieve complex goals? What is the nature of their consciousness, if any? The octopus challenges our very definition of intelligence and brain structure, forcing us to reconsider the evolutionary paths to complex thought. Understanding the octopus brain could reveal entirely new paradigms of cognition, but for now, their alien brilliance remains largely an enigma. 17. Why yawning is contagious. Yawning is an involuntary reflex, an ancient, universal behavior observed across many species, yet the reason it's so incredibly contagious among humans remains a fascinating puzzle. Seeing someone yawn, hearing a yawn, or even just reading about yawning can trigger one ourselves. This social contagion is not fully understood. Is it a primitive form of empathy, a way to synchronize group behavior, or a signal of shared mental state? Some theories suggest it's linked to social bonding, as contagion is often stronger among individuals who are emotionally close. Others propose it's a form of nonverbal communication, perhaps signaling fatigue or boredom. Neurologically, it's thought to involve mirror neurons and specific brain regions associated with empathy, but the precise cascade of events that translates an observed yawn into a felt urge to yawn and the evolutionary advantage of this phenomenon are still subjects of ongoing research. The simple, contagious yawn is a surprisingly complex window into our social and neurological wiring. 18. Immune system memory precision. Our immune system is a marvel of biological engineering, capable of remembering past invaders and launching a faster, more effective defense upon re-exposure. This immune memory is the foundation of vaccination, yet the precision and longevity of this memory are still not fully understood. How do specialized cells, like memory B cells and key cells, persist in the body for decades, sometimes even a lifetime, ready to spring into action against a specific pathogen they encountered years ago? What molecular signals maintain their dormancy and then activate them so rapidly and accurately when needed? We know these cells undergo a process of clonal expansion and affinity maturation, but the exact mechanisms that ensure such highly specific and enduring recall, preventing future infections, are still being elucidated. The immune system's library of past threats is incredibly vast and remarkably accurate, a biological feat whose full genius we are still working to comprehend. 19. Autoimmune triggers. In autoimmune diseases, the immune system, designed to protect us from external threats, mistakenly turns against the body's own tissues, leading to chronic inflammation and damage. Conditions like rheumatoid arthritis, lupus, and multiple sclerosis are devastating, but what precisely triggers this catastrophic self-attack remains one of medicine's most pressing questions. We know that genetics play a role, making certain individuals more susceptible, and environmental factors like infections, stress, or exposure to certain chemicals are also implicated. However, the exact combination of genetic predisposition and environmental triggers that pushes the immune system past a critical threshold, causing it to lose tolerance for self, is largely unknown. Why does the immune system suddenly perceive healthy cells as foreign invaders? Unraveling these complex triggers is crucial for developing effective prevention and treatment strategies for the millions worldwide living with autoimmune conditions. 19. Autoimmune triggers. In autoimmune diseases, the immune system, designed to protect us from external threats, mistakenly turns against the body's own tissues, leading to chronic inflammation and damage. Conditions like rheumatoid arthritis, lupus, and multiple sclerosis are devastating, but what precisely triggers this catastrophic self-attack remains one of medicine's most pressing questions. We know that genetics play a role, making certain individuals more susceptible, and environmental factors like infections, stress, or exposure to certain chemicals are also implicated. However, the exact combination of genetic predisposition and environmental triggers that pushes the immune system past a critical threshold, causing it to lose tolerance for self, is largely unknown. Why does the immune system suddenly perceive healthy cells as foreign invaders? Unraveling these complex triggers is crucial for developing effective prevention and treatment strategies for the millions worldwide living with autoimmune conditions. 20. Allergies increasing globally. Over the past few decades, there has been a dramatic and puzzling increase in the prevalence of allergies and allergic diseases, such as asthma, eczema, and food allergies, particularly in developed nations. This global rise cannot be fully explained by genetics alone, suggesting significant environmental contributions. The leading hypothesis is the hygiene hypothesis, which posits that reduced exposure to microbes and infections in early childhood, due to cleaner environments and widespread antibiotic use, prevents the immune system from developing properly, making it hypersensitive to harmless substances. However, this theory alone doesn't fully account for all aspects of the increase, nor does it explain why some allergies are rising faster than others. Other factors like diet, pollution, vitamin D deficiency, and changes in the microbiome are also being investigated. The exact reasons behind this modern epidemic of allergic reactions remain a complex, multifaceted puzzle, challenging our understanding of immune system development in a rapidly changing world. 21. Cancer spontaneous remission. Cancer is a formidable adversary, and while medical treatments have advanced significantly, one of the most astonishing and inexplicable phenomenon is spontaneous remission. This rare event occurs when a cancer partially or completely disappears without any medical treatment, or with treatment that is considered inadequate to achieve such a result. While extremely uncommon, these cases defy conventional medical understanding. How does the body's own immune system, which typically fails to recognize and eliminate cancer cells, suddenly mount an effective self-directed attack? Is it a potent but unknown activation of anti-tumor immunity? A sudden beneficial mutation in the cancer cells themselves? Or perhaps an intricate interplay of psychological factors, nutritional changes, or even undiscovered biological mechanisms? Each documented case serves as a profound reminder of the body's mysterious healing potential and offers tantalizing clues that, if fully understood, could revolutionize cancer therapy. For now, spontaneous remission remains a medical enigma, a beacon of hope in the face of despair. 23. Sudden arrhythmic death syndrome. Sudden arrhythmic death syndrome, or SADS, is a tragic and perplexing condition where seemingly healthy individuals, often young adults or athletes, die suddenly due to an unexpected cardiac arrest, with no apparent cause found during autopsy. It's often linked to inherited heart conditions that affect the heart's electrical activity, such as long QT syndrome or Brugada syndrome, but these conditions are not always diagnosed prior to the fatal event. The mystery lies in why these underlying conditions, which might have been asymptomatic for years, suddenly trigger a fatal arrhythmia. What is the precise trigger that causes the heart's electrical system to go haywire without warning? Is it extreme physical exertion, stress, electrolyte imbalances, or perhaps an unknown genetic modifier? The suddenness and unexpectedness of SADS, leaving no clear structural damage to the heart, highlight the intricate and delicate balance of our cardiac electrical system and the profound questions that remain about its vulnerabilities. 23. Chronic fatigue syndrome. Chronic fatigue syndrome, or myalgic encephalomyelitis, ME/CFS, is a debilitating and complex illness characterized by extreme fatigue that isn't relieved by rest, post-exertional malaise, and a host of other symptoms, including cognitive dysfunction, pain, and sleep disturbances. Despite its profound impact on millions of lives, the underlying cause of ME/CFS remains unknown and highly controversial. Is it an immunological disorder, a persistent viral infection, a mitochondrial dysfunction, a neurological impairment, or a combination of these factors? Researchers have observed various physiological abnormalities in ME/CFS patients, including immune system dysregulation, autonomic nervous system dysfunction, and gut microbiome alterations. But no single biomarker or definitive cause has been identified. The lack of a clear diagnostic test or universally effective treatment underscores how much we still have to learn about this enigmatic condition, leaving patients in a medical limbo while science grapples with its intricate pathology.
24. Placebo surgeries working. Building upon the enigma of the general placebo effect, the phenomenon of placebo surgeries achieving positive outcomes is even more astonishing. In these studies, patients undergo a sham surgical procedure, often involving incisions but no actual operative intervention, and report comparable improvements to those receiving real surgery for conditions like knee pain, back pain, or even angina. This raises profound questions about the nature of healing, the power of expectation, and the limitations of our understanding of the body's self-repair mechanisms. How can the belief that surgery has occurred induce genuine physiological changes that mimic the effects of an actual operation? Is it purely psychological, altering pain perception, or does the ritual of surgery itself trigger deeper, unknown healing pathways? The effectiveness of placebo surgeries challenges the very foundations of medical intervention, suggesting that the mind's capacity to influence the body's recovery is far more potent and mysterious than we currently comprehend. 25. Consciousness after anesthesia. Anesthesia is a marvel of modern medicine, allowing us to undergo invasive procedures without pain or memory. It works by temporarily suppressing brain activity, yet the precise mechanism by which it induces unconsciousness and whether consciousness truly vanishes completely remains a profound scientific puzzle. We know that anesthetics target specific neurotransmitter systems, but how this translates into the subjective experience of losing consciousness is still debated. Furthermore, there are intriguing reports of awareness under anesthesia, where patients recall events from surgery despite being supposedly unconscious, raising questions about the depth and nature of anesthetic-induced unconsciousness. Does consciousness simply dim, or does it fragment? And how does it fully re-emerge seamlessly once the drugs wear off? The transition between conscious and unconscious states, expertly manipulated by anesthesiologists every day, is a complex dance of brain chemistry and electrical activity whose full choreography we are still struggling to understand. 26. Phantom limb sensations. For individuals who have lost a limb, the vivid and often painful sensation that the missing limb is still present, known as phantom limb sensation, is a perplexing neurological phenomenon. Patients report feeling the limb, experiencing itching, tingling, or even excruciating pain in a body part that no longer exists. This challenges our understanding of how the brain maps the body and processes sensory information.
Is it due to the brain's wiring for the limb remaining intact, leading to a disconnect between sensory input and the brain's internal representation? Is it caused by reorganization in the somatosensory cortex, where adjacent areas invade the cortical map of the missing limb? Or are severed nerve endings at the stump generating signals that the brain misinterprets? While theories abound, the exact mechanisms by which the brain continues to feel a limb that is physically gone and how to alleviate the associated pain remain a profound mystery, highlighting the intricate and sometimes confusing ways our brains construct reality. 27. Gut-brain connection depth. The idea that our gut and brain are connected has moved from folk wisdom to scientific fact. But the true depth and complexity of this gut-brain axis are still being uncovered. It's far more than just butterflies in your stomach when you're nervous. The gut has its own intricate nervous system, the enteric nervous system, sometimes called the second brain, which communicates constantly with the central nervous system. But how exactly the composition of our gut microbiome, the trillions of bacteria living in our intestines, influence our mood, cognition, behavior, and even susceptibility to neurological disorders like Parkinson's or Alzheimer's? We know these microbes produce neurotransmitters and other compounds, but the precise pathways, the signaling molecules, and the full extent of their influence on brain function are still largely unknown. Understanding this intricate dialogue could revolutionize treatments for mental health and neurological conditions, but for now, the gut-brain connection remains a frontier of profound biological mystery. 28. Microbiome's full role. Beyond its connection to the brain, the human microbiome, the vast ecosystem of bacteria, viruses, fungi, and other microorganisms living in and on our bodies, plays an astonishingly diverse and vital role in our health, much of which is still a mystery. We know it aids in digestion, synthesizes vitamins, and helps train our immune system. But what are the full implications of its composition for our metabolism, propensity for obesity, susceptibility to allergies, or even our response to medications? How do subtle shifts in microbial balance influence chronic diseases like diabetes, inflammatory bowel disease, or even cancer? The sheer diversity and individuality of each person's microbiome makes it incredibly challenging to establish cause and effect relationships. We are only just beginning to map this internal universe, and the full extent of its influence on human physiology and disease prevention, as well as how to optimally manipulate it for health, remains a grand biological frontier. 29. Why humans have emotions. Emotions are fundamental to the human experience, coloring our perceptions, driving our decisions, and shaping our relationships. But why do we have them? From a purely evolutionary standpoint, while emotions like fear and anger have clear survival benefits, the purpose of complex emotions like joy, grief, or awe is less straightforward. Are emotions simply sophisticated physiological responses to external stimuli, or do they serve deeper cognitive and social functions? How do they arise from the interaction of brain regions, neurotransmitters, and body sensations? And why do they manifest in such a universal yet individually varied way? While we can describe the neural correlates of emotions and their behavioral expressions, the precise mechanisms by which subjective feelings emerge and their full evolutionary rationale remain profound questions. The raw, visceral power of human emotion is a mystery woven into the very fabric of our being.
30. Origin of language. Language is arguably the most defining characteristic of humanity, allowing for complex thought, cultural transmission, and unprecedented cooperation. Yet, its origin remains one of the greatest unsolved problems in evolutionary anthropology and linguistics. When, why, and how did our ancestors develop the capacity for symbolic communication, grammar, and syntax? Was it a sudden mutation, a gradual accumulation of cognitive abilities, or a byproduct of other evolutionary pressures, like tool-making or social complexity? Did it emerge from gestural communication, vocalizations, or a combination?
The lack of direct fossil evidence for language makes it incredibly challenging to reconstruct its evolutionary path. While theories abound, from proto-language stages to the role of specific brain structures, the moment our ancestors first uttered meaningful words, transforming grunts and calls into a structured system of communication, is a profound mystery lost to the mists of time. 31. Why we have dominant hands. The vast majority of humans, around 90%, are right-handed, with a smaller percentage being left-handed and a very small fraction ambidextrous. This phenomenon of handedness is almost unique to humans among primates, yet its evolutionary origin and precise neurological basis remain a puzzle. Why is there such a strong bias towards right-handedness? Is it purely genetic, a byproduct of brain lateralization where different functions are specialized in different hemispheres? Or are environmental factors, such as cultural pressures or early developmental experiences, more influential? While the left hemisphere of the brain typically controls language and is dominant in right-handers, the exact causal relationship between brain asymmetry and handedness is not fully understood. Why didn't evolution favor ambidexterity, which might seem more advantageous? The mystery of why we reach for the world predominantly with one hand over the other is a subtle yet pervasive question about human brain development and evolution. 32. Human bipedal evolution oddities. The evolution of bipedalism, walking upright on two legs, was a defining moment in human history, freeing our hands for tool use and carrying. However, it came with significant trade-offs and oddities that still puzzle scientists. Why did our ancestors transition to bipedalism in the first place, especially when it made them slower than quadrupeds and more prone to back problems and childbirth difficulties? What was the immediate evolutionary pressure that outweighed these disadvantages? The fossil record suggests a complex, mosaic evolution, with different species exhibiting varying degrees of bipedalism. Furthermore, the human pelvis, spine, and feet underwent dramatic restructuring, leading to unique vulnerabilities. While theories range from savanna adaptation to carrying food or thermoregulation, the precise sequence of events, the specific environmental catalysts, and the full suite of advantages that drove this fundamental shift in locomotion remain subjects of intense debate and ongoing discovery. 34. Human hairlessness. Compared to our primate relatives, humans are remarkably hairless, covered mostly in fine vellus hair rather than thick fur. The evolutionary reasons behind this striking hairlessness remain a significant mystery. Why did we shed our fur? One prominent theory, the savanna hypothesis, suggests it helped with thermoregulation in hot, open environments, allowing sweat to evaporate more efficiently. Another, the aquatic ape hypothesis, proposes it was an adaptation to a semi-aquatic phase in our evolution, similar to marine mammals. Other ideas include reducing parasite load or signaling sexual maturity. However, each theory faces challenges and doesn't fully account for the complete loss of fur across the entire body. Furthermore, the genetic mechanisms that led to this reduction in hair density are still being investigated. Our smooth skin is a defining feature, yet the precise evolutionary path that led to this unique characteristic is still a captivating and unresolved question. 35. Mystery of sperm competition. In many species, including humans, females often mate with multiple males, leading to a phenomenon known as sperm competition, where the sperm from different males literally compete to fertilize an egg. While the existence of this competition is clear, the full extent of its evolutionary impact and the precise mechanisms involved are still mystery. How do sperm from one male gain an advantage over another? Is it sheer numbers, speed, longevity, or specific biochemical interactions with the female reproductive tract? Some theories suggest that certain sperm morphology or behaviors, like forming sperm trains, are adaptations for competition, but the evidence is often equivocal. Furthermore, the female reproductive tract itself plays an active and still poorly understood role in selecting or filtering sperm. The intricate molecular and physiological battle that unfolds within the female body, determining which sperm ultimately succeeds, is a microscopic drama whose full script remains largely unwritten.
36. Why men have nipples. One of the most common and seemingly inexplicable anatomical features in human males is the presence of nipples. They serve no known physiological function in men, yet they are universally present. The scientific explanation is straightforward. During early fetal development, all human embryos are anatomically undifferentiated, and nipples form before the sex chromosomes activate to trigger the development of male or female reproductive organs. So, men have nipples because they are a default, vestigial structure from early development. However, this explanation, while accurate, doesn't fully address the evolutionary question. Why hasn't natural selection eliminated a seemingly useless feature that might, in rare cases, even be susceptible to cancer? Is the cost of maintaining them so negligible that there's no selective pressure against them? Or do they serve some currently unknown subtle function, perhaps related to genetic linkage with other crucial developmental genes? The male nipple, a seemingly trivial detail, points to deeper questions about evolutionary efficiency and developmental pathways. 37. Origin of homosexuality in evolution. From an evolutionary perspective, the persistence of homosexuality across human populations and in many animal species presents a significant puzzle. If the primary driver of evolution is the passing on of genes through reproduction, and homosexual individuals typically have fewer biological offspring, why has this trait not been selected out? Numerous theories attempt to explain this. The kin selection hypothesis suggests that homosexual individuals might contribute to the survival and reproduction of their relatives, and thus shared genes. Other ideas include antagonistic pleiotropy, where genes that increase reproductive fitness in heterosexual relatives might also predispose to homosexuality, or that it's a byproduct of complex genetic and environmental interactions that aren't directly selected for or against. The exact combination of genetic, hormonal, and environmental factors that contribute to sexual orientation and its evolutionary persistence remain one of the most complex and sensitive areas of biological inquiry. 38. Origin of left-handedness. While right-handedness dominates, a consistent minority of 10 to 15% of the human population is left-handed. Like handedness in general, the specific reasons for left-handedness are still not fully understood. Is it purely genetic, inherited through specific genes? Or is it influenced by prenatal factors like hormone exposure or uterine environment? While there's a higher concordance in identical twins, it's not 100%, indicating that genetics alone don't tell the whole story. Some theories suggest a link to brain organization, with left-handers often having more bilateral brain activity or different patterns of hemispheric dominance. Others propose that it might be a random developmental variation, or even a consequence of early brain injury. Despite centuries of observation, the precise developmental pathways and evolutionary pressures that lead to a significant portion of the population favoring their left hand continue to elude a comprehensive explanation, making it a subtle yet persistent mystery of human biology. 39. Why we get hiccups. Hiccups are a universal, often annoying, and usually harmless physiological phenomenon characterized by involuntary spasms of the diaphragm followed by a sudden closure of the vocal cords, producing the characteristic hic sound. While we know the basic mechanics, the precise purpose and trigger for hiccups remain a mystery. Why does this reflex exist at all? One prominent theory suggests it's a vestigial reflex, a remnant from our evolutionary past, perhaps linked to the breathing patterns of amphibians or the suckling reflex in mammalian infants. Another idea is that it helps to expel air from a distended stomach.
However, none of these explanations fully account for its erratic occurrence or its persistence across the lifespan. The specific neural pathways and the exact stimuli that initiate and terminate a bout of hiccups are still being investigated, leaving us with a common bodily quirk that defies a definitive scientific explanation. 40. Appendicitis causes. Appendicitis, the inflammation of the appendix, is a common and potentially life-threatening condition requiring urgent surgical intervention. Despite its prevalence, the exact cause of appendicitis is still not fully understood. The most accepted theory is that it occurs when the opening of the appendix becomes blocked, often by a piece of hardened stool, fecalith, swollen lymphoid tissue due to infection, or even parasites. This blockage leads to a buildup of mucus, increased pressure, and bacterial overgrowth, resulting in inflammation and infection. However, many cases of appendicitis occur without an obvious blockage, and some individuals with blockages never develop appendicitis. Why are some people more susceptible than others? What are the specific dietary, genetic, or microbial factors that predispose an individual to this painful and dangerous condition? The precise triggers that initiate this inflammation in a small, seemingly vestigial organ remain a significant clinical mystery. 41. Why we get goosebumps. Goosebumps, or piloerection, are a common physiological response where tiny muscles at the base of our hair follicles contract, causing our hairs to stand on end and our skin to pucker. While we know this reflex is triggered by cold, fear, or even powerful emotions like awe or nostalgia, its functional purpose in modern humans is largely vestigial and unexplained. In furry animals, piloerection serves to trap an insulating layer of air to keep warm, or to make the animal appear larger and more threatening. But for our relatively hairless species, goosebumps offer minimal insulation or intimidation. So why do we still get them? Is it a harmless evolutionary leftover, a ghost of our furry past? Or does it serve some subtle, unquantified purpose, perhaps related to our autonomic nervous system's response to emotional stimuli? The simple goosebump is a curious reminder of our ancient biological heritage, a reflex whose current utility in humans remains a physiological anachronism.
42. Why some people never get cavities. Dental caries, or cavities, are one of the most common chronic diseases globally, yet some individuals seem to have an extraordinary resistance, never developing a single cavity despite similar diets and oral hygiene habits as those prone to decay. The reasons behind this natural immunity are not fully understood. Is it purely genetic, with certain individuals inheriting teeth enamel that is inherently stronger or more resistant to acid erosion? Is it related to the unique composition of their oral microbiome, perhaps a protective balance of bacteria that inhibit cavity-causing strains? Or could it be differences in saliva composition, with some people producing saliva that is more effective at neutralizing acids or remineralizing enamel? While good oral hygiene and diet are crucial, the existence of cavity-proof individuals points to deeper, intrinsic biological factors that science is still working to identify. Unlocking these secrets could revolutionize preventative dental care for everyone. 43. Rare blood types origins. Beyond the familiar A, B, AB, and O blood groups and the Rh factor, there are dozens of other rare blood types, defined by unique combinations of antigens on the surface of red blood cells. The existence and origins of these rare types, some found in only a handful of individuals worldwide, present a fascinating genetic and evolutionary puzzle. How did such specific and uncommon antigenic profiles arise and persist in the human population? Are they remnants of ancient human migrations, adaptations to specific environmental pathogens, or simply random genetic mutations that have not been selected against? The rarity makes them incredibly difficult to study, but understanding their origins could provide insights into human genetic diversity, disease resistance, and population movements throughout history. Each rare blood type is a unique genetic fingerprint, a silent testament to the complex and still largely unwritten story of human evolution. 44. Spontaneous human combustion claims. Spontaneous human combustion, or SHC, is the alleged phenomenon of a living human body igniting and burning to ashes without an apparent external source of ignition. While widely dismissed by mainstream science as anecdotal and lacking credible evidence, and often attributed to misidentified fires or the wick effect, where body fat acts as fuel for external flame, the sheer consistency of some historical accounts and the unusual patterns of burning reported continue to fuel speculation. Why do some claims describe bodies reduced almost entirely to ash while surrounding objects remain relatively untouched? What could possibly initiate such an intense internal combustion without an external spark? The phenomenon defies our understanding of human physiology and thermodynamics, as the body is mostly water and not easily combustible. While scientists largely attribute these cases to external factors, the enduring popular fascination and the lack of a perfect, universally accepted explanation for every single reported instance keep SHC on the list of unexplained phenomena. 46. Ball lightning. Ball lightning is one of the most elusive and intriguing atmospheric phenomenon, described as a luminous, spherical object, often the size of a grapefruit or basketball, that appears during thunderstorms. Witnesses reported floating, hovering, or moving erratically, sometimes passing through walls or windows, before disappearing with a pop or fizzle. Despite thousands of anecdotal accounts spanning centuries, scientists have yet to definitively capture, reproduce, or fully explain ball lightning in a laboratory setting. What is its energy source? How does it maintain its shape and luminosity? Is it a plasma, a chemical reaction, or some other exotic form of matter? Theories range from vaporized silicon particles from the ground to complex electromagnetic phenomenon, but none have been conclusively proven. The fleeting, unpredictable nature of ball lightning makes it incredibly difficult to study, ensuring its place as one of nature's most enigmatic and beautiful electrical mysteries. 47. Earth's core exact temperature. We know Earth has a molten outer core and a solid inner core, composed primarily of iron and nickel. We also know it's incredibly hot, driving the planet's magnetic field and geological activity. However, determining the exact temperature of Earth's inner core remains a significant scientific challenge. We can't directly measure it, so scientists rely on seismic waves and high-pressure experiments to estimate it. Current models place it around 5,200 to 6,200 degrees Celsius, 9,392 to 11,192 degrees Fahrenheit, roughly the temperature of the sun's surface. But this is an estimate, with a margin of error due to the extreme pressures and temperatures involved in the models. Slight variations in these estimates can have profound implications for our understanding of the Earth's geodynamo, the flow of heat from the core, and the planet's overall evolution. The precise thermal conditions at the heart of our world remains a fierce and fundamental mystery. 47. Why Earth has so much water. Earth is the only known planet with abundant liquid water on its surface, a defining characteristic that makes life possible. But where did all this water come from? This question is a major unsolved puzzle in planetary science. The prevailing theory is that much of Earth's water was delivered by asteroids and comets during the late heavy bombardment era, after the planet's initial formation. However, recent research suggests that a significant portion of the water might have been present during Earth's accretion, locked within the planet's interior from the beginning. Furthermore, the precise timing and mechanisms of water delivery and retention are still debated. Why did Earth retain so much water while Venus, its sister planet, became a dry, scorching hellscape? The delicate balance of Earth's orbit, its size, and its geological activity all played a role, but the full story of our planet's watery origins is still being written.
48. Earth's magnetic field reversals. Earth's magnetic field acts as a protective shield, deflecting harmful solar radiation and allowing life to flourish. However, this field is not static. It regularly weakens, shifts, and occasionally undergoes a complete reversal, with the north and south magnetic poles swapping places. The perplexing part is that we don't fully understand why these reversals happen or what triggers them. We know the field is generated by the convection of molten iron in the Earth's outer core. But the complex dynamics that lead to a reversal, which can take thousands of years, are still a subject of intense research. What happens during a reversal? How weak does the field get? And what are the potential consequences for life on Earth, especially regarding increased radiation exposure? Predicting when the next reversal will occur and understanding its full implications remains a crucial and active area of geophysical inquiry. 49. Mass extinction triggers. Throughout Earth's history, there have been at least 5 major mass extinction events, periods where a significant portion of all species on the planet vanished in a relatively short geological time frame. While we have identified potential culprits for some, like the asteroid impact for the end Cretaceous extinction that wiped out the dinosaurs, the precise triggers and cascading effects for many others remain hotly debated. Was it massive volcanic eruptions, dramatic climate change, ocean anoxia, or a combination of multiple stressors? How do these events unfold on a global scale to cause such widespread devastation to ecosystems? Furthermore, understanding the exact mechanisms that push species past a critical threshold of survival during these cataclysms is crucial for assessing the current biodiversity crisis. The triggers of these ancient biological resets hold lessons for our present and future, but their full story is still being pieced together. 50. Origin of life. The question of how life first arose from non-living matter, a process known as abiogenesis, is arguably the most fundamental and profound scientific mystery. 4 billion years ago, Earth was a primordial soup of inorganic chemicals. Then, somehow, those chemicals organized themselves into self-replicating molecules, eventually leading to the first cells. But how did this improbable leap occur? What were the specific conditions on early Earth that fostered the formation of complex organic molecules? How did these molecules self-assemble into polymers, then acquire the ability to store information, like DNA or RNA, and catalyze reactions, like proteins? And most crucially, how did these disparate components come together to form a self-sustaining system enclosed within a membrane, giving rise to the first protocell? While scientists have made strides in creating some of life's building blocks in laboratory conditions, the precise sequence of events that led to the emergence of life from non-life remains a monumental, unanswered question. 51. RNA world uncertainties. One of the leading hypotheses for the origin of life is the RNA world hypothesis, which proposes that RNA, rather than DNA or proteins, was the primary genetic and catalytic material in early life forms. RNA can store genetic information, like DNA, and also catalyze biochemical reactions, like enzymes. This elegantly solves the chicken and egg problem of which came first, DNA or proteins. However, the RNA world hypothesis itself is full of uncertainties. How did the first RNA molecules spontaneously form under early Earth conditions? RNA is notoriously unstable and difficult to synthesize abiotically. What were the specific chemical pathways that allowed for the self-replication of these early RNA molecules without the aid of existing protein enzymes? And how did the transition from an RNA-dominated world to the DNA-protein world we see today occur? While compelling, the RNA world hypothesis still has many gaps, leaving us with a powerful yet incomplete picture of life's earliest stages. 52. How abiogenesis happened. Expanding on the origin of life, the precise step-by-step process of abiogenesis, the transition from non-living chemicals to the first living cells, remains frustratingly out of reach.
We can synthesize amino acids and nucleotides in a lab, but getting them to spontaneously assemble into complex, self-replicating, and metabolically active systems is another matter entirely. What were the energy sources that drove these early chemical reactions? Was it hydrothermal vents deep in the ocean, or warm little ponds on the surface? How did the first membranes form to compartmentalize these reactions, creating a distinct inside and outside? And what was the nature of the last universal common ancestor, or LUCA, from which all life today descended? The gap between complex organic chemistry and the simplest self-sustaining cellular life is vast, involving countless improbable steps. Reconstructing this precise sequence of events, a true recipe for life, is one of science's most ambitious and enduring challenges. 53. Cambrian explosion cause. Around 541 million years ago, Earth witnessed an astonishing burst of evolutionary innovation known as the Cambrian explosion. In a relatively short geological period, perhaps only 20 to 25 million years, almost all major animal phyla, representing a vast diversity of complex body plans, suddenly appeared in the fossil record. This rapid diversification of multicellular life is a profound evolutionary mystery. What triggered this explosion of complexity? Was it a sudden increase in atmospheric oxygen, allowing for more energetic metabolism? The evolution of key developmental genes? The emergence of predator-prey relationships, driving an evolutionary arms race? Or perhaps a significant environmental shift, like a snowball Earth event? The abruptness of the Cambrian explosion and the lack of clear ancestral forms preceding it challenges the gradualistic view of evolution and points to a missing piece in our understanding of life's trajectory.
54. First multicellular jump. Before the Cambrian explosion, life on Earth existed primarily as single-celled organisms for billions of years. Then, at some point, a monumental evolutionary leap occurred: the transition from single-celled to multicellular life. This was not a singular event, but one that happened independently multiple times across different lineages: plants, fungi, animals. The question is, why and how did cells, once fiercely independent, begin to cooperate and specialize to form complex, integrated organisms? What were the initial selective pressures that favored multicellularity over a solitary existence? How did cells overcome the challenges of communication, coordination, and resource allocation within a larger structure? And what were the genetic and developmental innovations that enabled this transition? The first jump to multicellularity was a paradigm shift in life's history, a fundamental reorganization that paved the way for all complex life, yet its precise origins remain a profound and enduring biological puzzle. 55. Deep-sea gigantism. In the abyssal depths of the ocean, where sunlight never penetrates and conditions are extreme, many creatures exhibit a peculiar phenomenon known as deep-sea gigantism. Isopods grow to the size of house cats, jellyfish can be massive, and some squid reach colossal proportions. Why do animals in the deep sea tend to grow much larger than their shallow water relatives? Several hypotheses attempt to explain this. The cold water theory suggests that lower temperatures lead to slower metabolic rates and longer lifespans, allowing for continuous growth. Another idea is that it's an adaptation to food scarcity, where a larger body size allows for greater energy storage or the ability to travel further to find food. Reduced predation pressure in the deep sea might also play a role. However, no single theory fully explains all instances of deep-sea gigantism, and the precise physiological and ecological drivers behind this intriguing evolutionary trend remain a subject of active research in the mysterious depths. 56. Tardigrade resilience. Tardigrades, also known as water bears or moss piglets, are microscopic invertebrates renowned for their astonishing resilience. These tiny creatures can survive conditions that would kill almost any other organism. Extreme temperatures, from near absolute zero to over 150 degrees Celsius, crushing pressures 6 times greater than the deepest ocean, intense radiation, the vacuum of space, and even complete dehydration for decades.
The mystery lies in precisely how they achieve this incredible feat of biological survival. What are the specific molecular mechanisms that allow their cells to endure such extreme stress? Researchers have identified unique proteins that form a protective glassy shield around their cellular machinery, and others that repair damaged DNA. But the full suite of adaptations and their precise interplay are still being unraveled. The tardigrade's unparalleled toughness challenges our understanding of biological limits and holds secrets that could revolutionize cryopreservation and space exploration. 56. Slime mold intelligence. Slime molds, specifically the single-celled organism Physarum polycephalum, are not animals, plants, or fungi, yet they exhibit astonishing problem-solving abilities that defy their simple biological structure. Without a brain or nervous system, a slime mold can navigate complex mazes, find the shortest path between food sources, and even create efficient network structures similar to human-designed roadmaps or railway systems. The mystery is, how does a single-celled organism, essentially a giant amoeba, demonstrate what appears to be a form of distributed intelligence or collective computation? How does it remember previous paths or learn from its environment? Is it through chemical signaling, physical vibrations, or some other unknown mechanism that allows its protoplasm to process information and make optimal decisions? The intelligence of slime molds challenges our anthropocentric definitions of cognition and forces us to reconsider the fundamental requirements for complex problem-solving in living systems. 59. Quantum measurement problem. Delving into the bizarre world of quantum mechanics, one of its most profound and unsettling mysteries is the quantum measurement problem. In the quantum realm, particles exist in a superposition of all possible states, simultaneously, until they are observed or measured. At that moment, the wave function collapses, and the particle chooses a single definite state. But why does measurement cause this collapse? What constitutes a measurement, or an observer? Is it the act of consciousness, the interaction with a classical measuring device, or something else entirely? The measurement problem highlights a fundamental disconnect between the probabilistic, fuzzy nature of the quantum world and the definite, objective reality we perceive. It suggests that reality itself might be observer-dependent at its most fundamental level, a concept that continues to provoke deep philosophical and scientific debate, challenging our very understanding of existence. 60. Quantum entanglement mechanism. Quantum entanglement is perhaps the most bizarre and counterintuitive phenomenon in physics. When two particles become entangled, they become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. The mystery is not whether it exists, it's been experimentally verified, but how it works. What is the mechanism that allows this instantaneous correlation without any apparent communication between the particles? Does it imply a deeper, non-local connection in the fabric of space-time, or a shared predetermined reality? While entanglement is a cornerstone of quantum computing, its underlying mechanism challenges our classical notions of cause and effect, locality, and the very nature of information.
61. Dark matter. When we look at galaxies and galaxy clusters, they behave as if they contain far more mass than we can see. Stars move too fast, and galaxies hold together too tightly to be accounted for by visible matter alone. This invisible, non-luminous substance, which doesn't interact with light or other electromagnetic forces, is what we call dark matter. It's estimated to make up about 27% of the universe's mass-energy budget, yet we have no idea what it actually is. Is it a new, undiscovered type of particle like WIMPs, weakly interacting massive particles, or axions? Or does it represent a modification to our understanding of gravity on cosmic scales? Despite decades of searching with highly sensitive detectors, dark matter particles have yet to be directly observed. Its elusive nature represents one of the biggest challenges in modern physics and cosmology, a massive unseen component shaping the universe that we cannot yet grasp. 62. Dark energy. If dark matter is mysterious, dark energy is even more so.
In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is not slowing down due to gravity, as expected, but is actually accelerating. This acceleration requires a repulsive force, a form of energy inherent in space itself, which we call dark energy. It's estimated to make up about 68% of the universe's total mass energy budget, making it the dominant component, yet its true nature is a complete enigma. Is it Einstein's cosmological constant, a constant energy density of empty space, or is it a dynamic, evolving field like quintessence? What physical properties does it possess? We don't know why it exists, what generates it, or how it exerts its repulsive effect. Dark energy is the biggest unknown in cosmology, a cosmic anti-gravity that is literally tearing the universe apart at an accelerating rate, and we have no fundamental theory to explain it. 63. Why gravity is so weak. Compared to the other fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity is astonishingly weak. For example, a tiny magnet can lift a paperclip against the gravitational pull of the entire Earth. This immense disparity in strength, known as the hierarchy problem, is a major unsolved puzzle in physics. Why is gravity so feeble? Is it because gravitons, the hypothetical particles that mediate gravity, are somehow leaking into extra dimensions as proposed by some theories of string theory or brane world cosmology? Or is there some fundamental reason related to the quantum nature of gravity that we don't yet understand? The weakness of gravity suggests that our current understanding of the universe's fundamental forces might be incomplete, perhaps indicating that there's more to reality than the 4 dimensions we perceive. 64. Matter-antimatter imbalance. According to our most successful theories, the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a burst of energy. If the universe started with equal amounts, everything should have annihilated, leaving behind a universe full of photons and no stars, planets, or us. Yet here we are, in a universe overwhelmingly dominated by matter. This baryon asymmetry problem is one of the most profound mysteries in cosmology. Where did the extra matter come from? What subtle yet crucial process allowed a tiny surplus of matter to survive the early universe's annihilation phase? Physicists have proposed various mechanisms such as CP violation or electrogenesis, but none have been definitively confirmed to explain the observed imbalance. The existence of everything we see, including ourselves, hinges on this tiny, inexplicable cosmic asymmetry. 66. Existence of multiverse. The concept of a multiverse, the idea that our universe is just one of many, perhaps infinitely many universes, is a fascinating and highly speculative idea that science still can't confirm or deny. While it sounds like science fiction, the idea arises naturally from several leading cosmological theories, such as inflationary cosmology, which suggests an eternal process of new universe creation, and string theory, which allows for a vast landscape of possible universes. If a multiverse exists, what would its nature be? Are these other universes entirely separate, or are they somehow connected to ours? Are their physical laws and constants the same or different? The challenge is that, by definition, we cannot observe or interact with other universes, making empirical verification incredibly difficult. The multiverse remains a captivating theoretical possibility, pushing the boundaries of what we consider reality, but firmly in the realm of the unproven. 66. Universe beginning mechanism. We know the universe began with the Big Bang, an incredibly hot, dense state approximately 13.8 billion years ago, from which it has been expanding and cooling ever since. But what caused the Big Bang? What mechanism initiated this cosmic genesis? Was it truly the beginning of everything, space, time, and matter, or was it a transition from a pre-existing state? Some theories propose a cyclical universe, where our universe is just one in an infinite series of Big Bangs and Big Crunches. Others suggest our universe emerged from a quantum fluctuation in a larger multiverse. The concept of nothing before the Big Bang is philosophically and scientifically challenging. We simply don't have a physics theory that can describe the conditions at the absolute singularity of time zero. The very first moments of creation, the ultimate origin of everything, remain the most fundamental and elusive mystery of cosmology. 67. Fine-tuning of constants. One of the most perplexing observations about our universe is the apparent fine-tuning of its fundamental physical constants. Values like the strength of gravity, the mass of an electron, the cosmological constant, or the strength of the strong nuclear force seem to be precisely calibrated to allow for the existence of stars, galaxies, and life. If these constants were even slightly different, the universe would be drastically different, perhaps collapsing instantly, flying apart too quickly, or failing to form complex atoms. The mystery is, why are these constants so perfectly tuned? Is it a cosmic coincidence, an indication of a divine creator, or evidence for the multiverse, where countless universes exist with different constants and we simply happen to be in one where life is possible? Science has no definitive answer, leaving the fine-tuning problem as a profound philosophical and scientific challenge that hints at a deeper, unknown order to the cosmos.
68. Cosmic inflation. The theory of cosmic inflation proposes that in the first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid exponential expansion. This theory elegantly solves several major problems with the standard Big Bang model, such as the horizon problem, why the universe is so uniform, and the flatness problem, why spacetime appears flat. However, the cause of inflation itself is still unknown. What was the inflaton field that drove this rapid expansion, and what are its physical properties? What triggered its onset, and, more importantly, its graceful exit, allowing the universe to transition to the slower expansion we see today? While inflation is a highly successful theoretical framework, the fundamental physics behind this explosive early growth remains elusive. Unraveling the mechanism of cosmic inflation would provide a crucial missing piece in our understanding of the universe's earliest moments. 69. True nature of time. Time is perhaps the most fundamental and yet least understood aspect of our reality. We experience it as a relentless, unidirectional flow from past to present to future, a dimension through which all events unfold. But what is time fundamentally? Is it a fundamental property of the universe, an independent dimension like space? Or is it an emergent phenomenon, an illusion arising from the way our brains process information or the way entropy increases? Einstein showed that time is relative, affected by speed and gravity, but this doesn't explain its intrinsic nature. Does time truly flow? And if so, what does it flow relative to? Is it a continuous fabric, or is it quantized, existing in discrete, indivisible units? The true nature of time, its very essence, remains a profound philosophical and scientific mystery, challenging our most basic perceptions of existence. 69. Arrow of time. One of the most perplexing aspects of time is its arrow. Why does time only flow forward? The fundamental laws of physics at the microscopic level are largely time-symmetric. They work just as well backward as forward. Yet, in our macroscopic world, time clearly has a direction. Eggs break but don't spontaneously reassemble. We remember the past but not the future. And entropy always increases. This arrow of time is typically explained by the second law of thermodynamics, which states that the total entropy, disorder, of a closed system can only increase over time. But this then raises the question, why did the universe begin in such a highly ordered, low-entropy state? Was the Big Bang itself the ultimate source of the arrow of time? The unidirectional flow of time is so ingrained in our experience, yet its fundamental origin remains a deep and unresolved puzzle at the intersection of physics and cosmology. 70. Why time flows forward. Building on the arrow of time, the question of why time flows forward and not backward continues to baffle physicists and philosophers alike. As mentioned, most fundamental laws of physics are time reversible.
If you watch a video of billiard balls colliding and then play it backward, it still looks physically plausible. Yet, we never see macroscopic events reverse spontaneously. The most common explanation ties it to increasing entropy. The universe started in a very low entropy state, and as it evolves, entropy inevitably increases, giving time its direction. But this explanation doesn't explain why the initial state was so low in entropy. Was it a cosmic initial condition? Is our perception of time linked to the thermodynamic arrow, or is there a deeper, unknown mechanism at play? The seemingly simple fact that time moves only forward is a profound cosmic mystery, challenging our understanding of causality and the universe's origin. 70. Black hole singularities. At the heart of every black hole, according to Einstein's theory of general relativity, lies a singularity, a point of infinite density and zero volume, where space-time curvature becomes infinite. This mathematical prediction represents a breakdown of our current understanding of physics. What actually happens at this point? Does matter truly get crushed to an infinitely small size? If so, what are the physical properties of such an object? The existence of singularities implies that general relativity is incomplete and needs to be reconciled with quantum mechanics to describe what happens at these extreme conditions. A quantum theory of gravity might resolve the singularity problem, perhaps suggesting that there's a minimum possible size for matter, or that space-time itself has a granular structure. Until then, black hole singularities remain theoretical constructs, representing a profound boundary beyond which our current laws of physics cease to make sense. 74. Information paradox. The black hole information paradox is one of the most contentious and profound problems in theoretical physics, pitting quantum mechanics against general relativity. According to quantum mechanics, information can never be truly destroyed. However, general relativity suggests that anything falling into a black hole is lost forever, effectively destroying its information as the black hole eventually evaporates via Hawking radiation. If information is truly lost, it violates a fundamental principle of quantum mechanics. So, what happens to the information of matter that falls into a black hole? Does it somehow escape in a scrambled form through Hawking radiation? Is it stored on the event horizon? Or is the information truly destroyed, requiring a radical revision of quantum theory? The information paradox challenges the very foundations of our understanding of the universe, suggesting a deep inconsistency between our two most successful physical theories. 75. What happens inside a black hole? Beyond the event horizon, the point of no return, what truly happens inside a black hole remains a realm of pure theoretical speculation and profound mystery. General relativity predicts that anything crossing the event horizon is inexorably drawn towards the singularity, where it is crushed to infinite density. But this is a classical description. A complete understanding would require a theory of quantum gravity, which we don't yet have. Do space and time swap roles inside? Is it a portal to another universe? Do new exotic states of matter form? The intense gravitational forces and the breakdown of space-time at the singularity mean that our current physics cannot accurately describe the interior. While we can observe their effects from the outside, the inner workings of a black hole, the ultimate fate of anything that falls in, and the true nature of its singularity are perhaps the most extreme frontiers of the unknown.
75. Fast radio bursts. Fast radio bursts, or FRBs, are incredibly powerful, millisecond-long flashes of radio waves originating from distant galaxies. First detected in 2007, they are among the most energetic phenomena in the universe, releasing more energy in a fraction of a second than the sun does in a day. The mystery is, what causes them? We've detected hundreds of them, some repeating, others appearing only once, but their source remains elusive. Are they caused by highly magnetized neutron stars, magnetars undergoing starquakes, colliding black holes, or something even more exotic, like hypothetical blitzers or even intelligent alien signals? While magnetars are currently the leading candidate, they don't explain all observed characteristics, especially for the non-repeating bursts.
The precise physical mechanisms behind these enigmatic cosmic flashes and the extreme environments that produce them are still a major puzzle for astrophysicists. 76. Tabby's star dimming. Tabby's star, officially KIC 8462852, is a main sequence star located about 1,470 light-years from Earth that exhibits highly unusual and dramatic dimming events. Unlike typical exoplanet transits, which cause predictable, shallow dips in brightness, Tabby's star has shown irregular, non-periodic dimming of up to 22%, lasting for days or weeks. The mystery is, what is causing these bizarre fluctuations? Initial theories included a swarm of comets, but the sheer amount of material required is immense. Other hypotheses range from a disintegrating planet, a distorted star, or even alien megastructures, a Dyson sphere-like construction built by an advanced civilization. While the alien megastructure theory is highly speculative, no natural explanation has fully accounted for the unique and complex light curve of Tabby's star. Its inexplicable behavior makes it one of the most intriguing and mysterious objects in the observable universe. 77. Alien life absence. Fermi paradox. The universe is vast, ancient, and filled with billions of galaxies, each containing billions of stars. Many of these stars are likely to have Earth-like planets. Given these immense numbers, the probability of intelligent alien life evolving somewhere else seems incredibly high. So, where is everybody? This stark contradiction between the high probability of extraterrestrial intelligence and the lack of observational evidence is known as the Fermi paradox. Why haven't we found any signs of alien civilizations, their probes, or their signals? Is it because intelligent life is incredibly rare? Do civilizations tend to destroy themselves before achieving interstellar travel? Are there great filters that prevent life from reaching advanced stages? Or are we simply looking in the wrong way or in the wrong place? The silence of the cosmos is one of the most profound and unsettling mysteries, forcing us to confront our place and uniqueness, or lack thereof, in the universe. 78. UFO/UAP physics anomalies. For decades, reports of unidentified flying objects, UFOs, have been largely dismissed. However, in recent years, with declassified military footage and credible eyewitness accounts, the term has shifted to unidentified aerial phenomenon, UAPs. The mystery now focuses on the reported physics anomalies of these objects. They are described as moving at hypersonic speeds without a sonic boom, making instantaneous turns at extreme g-forces, hovering motionless, or descending from high altitudes to sea level in seconds, all without visible means of propulsion. These reported capabilities defy our current understanding of aerodynamics and propulsion. While many UAPs are eventually identified as conventional aircraft, drones, or atmospheric phenomenon, a small fraction remains unexplained. What are these objects, and how do they perform maneuvers that appear to violate known laws of physics? The scientific community is grappling with the need for rigorous data collection to address these persistent and highly intriguing observations. 79. Dyson sphere-like signals. A Dyson sphere is a hypothetical megastructure that an advanced alien civilization might build around a star to harness its entire energy output. Such a structure would emit a distinctive infrared signature as it radiates waste heat. While no definitive Dyson sphere has been found, some astronomical observations have hinted at patterns that could potentially be interpreted as such. For example, the aforementioned Tabby star, with its inexplicable dimming, was briefly considered a candidate. The mystery is not whether we found one, but whether such signals, or other signs of advanced technological civilizations, exist in the cosmic background. Are we missing subtle clues? How would we distinguish a natural astronomical phenomenon from a truly artificial construct on a stellar scale? The search for Dyson sphere-like signals is a frontier of astrobiology and SETI, pushing us to consider the ultimate potential of alien intelligence even as we struggle to define what such evidence might look like. 80. Rogue planets' origins. Rogue planets, also known as free-floating planets or unbound planets, are celestial bodies with planetary mass that do not orbit a star. They drift through interstellar space, unattached to any stellar system. The existence of these objects, confirmed by gravitational microlensing and direct imaging, raises a significant mystery. How do they form? Are they ejected from their home star systems due to gravitational interactions with other planets or passing stars? Or do they form independently in interstellar space, similar to stars, but simply fail to gather enough mass to ignite fusion? The prevalence of these rogue planets suggests they might outnumber stars in our galaxy, making their formation mechanism a crucial piece of the planetary puzzle. Understanding their origins could reshape our models of planet formation and evolution, revealing a vast, unseen population of worlds adrift in the cosmic ocean. 81. Oort cloud not yet observed. The Oort cloud is a hypothetical spherical shell of icy planetesimals thought to be the source of long-period comets located at the outermost reaches of our solar system, extending perhaps a third of the way to the nearest star. Despite being theorized for decades and providing a compelling explanation for comet origins, the Oort cloud itself has never been directly observed. Its objects are too small, too far away, and too faint to be detected by current telescopes. The mystery is whether it truly exists as theorized or if its properties are different. What is its exact size, shape, and composition? How many objects does it contain, and how did they form so far from the Sun? The Oort cloud represents the last major unobserved structure of our solar system, a vast, dark, icy reservoir whose secrets remain hidden, waiting for a future generation of telescopes to finally pierce its enigmatic veil.
82. Why Venus rotates backwards. Venus, Earth's closest planetary neighbor, stands out among the planets in our solar system for one peculiar reason. It rotates backwards, or retrogrades, meaning it spins in the opposite direction to its orbit around the Sun. Most planets, including Earth, rotate counterclockwise when viewed from above their north pole. Venus rotates clockwise. This retrograde rotation is a major anomaly, and its cause is still a mystery. The leading theory suggests that Venus initially rotated in the prograde direction, but a massive impact event early in its history, or a complex interplay of atmospheric tides and gravitational forces from the Sun, gradually flipped its rotation. However, no single model fully explains the current slow retrograde spin. Understanding Venus's unique rotation could provide crucial insights into planetary formation and evolution. But for now, it remains the solar system's most stubborn rotational puzzle. 83. Neptune's extreme winds. Neptune, the outermost gas giant in our solar system, is characterized by the most violent winds of any planet, reaching speeds of up to 2,100 kilometers per hour, 1,300 miles per hour, faster than the speed of sound on Earth. These incredible wind speeds, which are far greater than those on Jupiter or Saturn, are a major mystery. Given Neptune's great distance from the Sun and its relatively low internal heat, what powers these supersonic atmospheric currents? Why isn't its atmosphere frozen in place? Theories suggest that a combination of factors might be at play: a lack of solid surface to create friction, the planet's slow rotation, and perhaps an unknown internal heat source driving convection. However, the precise mechanisms that generate and sustain these astonishingly powerful winds, making Neptune the windiest planet, are still not fully understood, leaving us to marvel at its turbulent, distant beauty. 84. Uranus's tilt. Uranus is famous for its extreme axial tilt. It rotates almost completely on its side, with its axis tilted by about 98 degrees relative to its orbital plane. This means that during its 84-year orbit, each pole experiences decades of continuous sunlight followed by decades of continuous darkness. This dramatic tilt is a profound anomaly among the solar system's planets, and its origin is a major mystery.
The most widely accepted theory is that a massive collision with an Earth-sized protoplanet early in the solar system's history knocked Uranus onto its side. However, simulations struggle to perfectly reproduce the current tilt and the planet's moon system, which also orbits on the same tilted plane. Could it have been multiple smaller impacts or a complex gravitational interaction with other gas giants? The unique orientation of Uranus challenges our understanding of planetary formation and the violent history of our solar system. 85. Jupiter's Great Red Spot's persistence. Jupiter's Great Red Spot is an iconic feature, a colossal anticyclonic storm larger than Earth that has been observed for at least 350 years, making it the longest-lasting storm in the solar system. The mystery is, why has it persisted for so long? What powers this vortex, preventing it from dissipating like other storms on Jupiter and Earth? Theories suggest that the spot's immense size avoids interaction with other atmospheric features that would break it up. Its position between opposing jet streams might also contribute, with the larger currents feeding energy into the storm. However, the precise mechanisms that sustain its incredible longevity and how it continues to generate its vibrant red color are still subjects of intense research. While observations show it is slowly shrinking, the Great Red Spot remains a magnificent and enduring testament to the turbulent, enigmatic power of Jupiter's atmosphere. 86. Saturn's hexagon. At the North Pole of Saturn, a truly bizarre and unique atmospheric feature exists, a persistent hexagonal cloud pattern, approximately 30,000 kilometers, 20,000 miles across, with sides about 14,500 kilometers, 9,000 miles. This six-sided jet stream is unlike anything else seen elsewhere in the solar system, and its origin is a profound mystery. How does Saturn's atmosphere spontaneously generate such a perfect geometric shape? Scientists believe it's a standing wave pattern in the planet's upper atmosphere, similar to how fluids behave in rotating systems. But the exact mechanism that stabilizes this hexagon and prevents it from dissipating or adopting other shapes is still unknown. It's a complex interplay of fluid dynamics, atmospheric convection, and the planet's rapid rotation. The Saturnian hexagon is a mesmerizing natural wonder, a testament to the strange and beautiful physics that can emerge in the atmospheres of gas giants. 88. Enceladus plume mechanism. Saturn's moon Enceladus is one of the most exciting places in the solar system for the search for extraterrestrial life, thanks to its subsurface ocean of liquid water. This ocean periodically erupts into space through massive geysers or plumes emanating from tiger stripes at its south pole. The mystery is, what powers these plumes? What is the precise mechanism that generates and sustains the heat necessary to keep the ocean liquid and drive these powerful eruptions? Tidal forces from Saturn are thought to play a major role, flexing Enceladus and generating heat. However, models struggle to explain the sheer amount of heat observed and how it's concentrated at the South Pole. Is there an additional heat source, perhaps radioactive decay in its core? Understanding the plume mechanism is crucial for assessing Enceladus's habitability, as these eruptions provide samples of the moon's potentially life-supporting ocean directly into space. 88. Europa's ocean chemistry. Jupiter's moon Europa is another prime candidate for hosting extraterrestrial life, as evidence strongly suggests it harbors a vast, salty ocean beneath its icy shell, perhaps twice the volume of all Earth's oceans combined. The mystery lies in the precise chemistry of this ocean. What are its exact chemical composition and salinity? Is it rich in the necessary chemical building blocks and energy sources that could support life, similar to Earth's hydrothermal vents? We've detected evidence of salts and organic molecules on Europa's surface, but the direct sampling of its subsurface ocean remains a future endeavor. Understanding the ocean's chemistry, its pH, the presence of oxidants and reductants, and the availability of nutrients is paramount to determining its habitability. Europa's hidden ocean holds the promise of life beyond Earth, but its fundamental chemical secrets remain locked beneath miles of ice.
89. Titan's methane cycle. Saturn's largest moon, Titan, is the only moon in our solar system with a dense atmosphere and stable bodies of liquid on its surface. But these liquids are not water. They are lakes and rivers of liquid methane and ethane. Titan experiences a methane cycle analogous to Earth's water cycle, with clouds, rain, and evaporation. The mystery lies in the source and long-term sustainability of this methane. Methane in Titan's atmosphere is constantly broken down by sunlight, meaning there must be a continuous replenishment. Is it generated by geological processes in Titan's interior, perhaps through cryovolcanism, ice volcanoes, or hydrothermal activity? Or is it a byproduct of exotic forms of subsurface life? While some theories point to internal geological activity, the precise mechanisms of methane regeneration and the full dynamics of Titan's bizarre hydrological cycle are still being unraveled, painting a picture of a truly alien world. 90. Why the sun's corona is hotter than its surface. The sun's surface, the photosphere, has a temperature of about 5,500 degrees Celsius, 9,940 degrees Fahrenheit. Logically, one would expect temperatures to decrease further away from the heat source. Yet the sun's outermost atmosphere, the corona, is incredibly hot, reaching millions of degrees Celsius, hundreds of times hotter than the surface below it. This coronal heating problem is one of the longest-standing mysteries in solar physics. What mechanism transfers such immense energy from the relatively cooler surface to the superheated corona? Theories include magnetic reconnection events, where magnetic field lines break and reconnect, releasing energy, or various types of waves, example Alfvén waves, propagating through the solar atmosphere. However, no single theory has definitively explained the full phenomenon. Unlocking the secret of coronal heating is crucial for understanding space weather, solar flares, and the very dynamics of our star. 91. Solar cycle timing. The sun isn't static. It undergoes an approximately 11-year cycle of activity, characterized by waxing and waning numbers of sunspots, solar flares, and coronal mass ejections. This solar cycle profoundly influences space weather and can affect Earth's technology and climate. The mystery is, what drives this cycle and why is its timing so variable? While we know it's related to the sun's complex magnetic field, generated by the dynamo effect in its interior, the precise mechanisms that cause the field to flip and regenerate over this specific period are not fully understood. Why is it roughly 11 years, and why can individual cycles vary in length and intensity? Predicting the solar cycle's behavior is incredibly challenging, yet crucial for space exploration and protecting our planet's infrastructure. The sun's rhythmic heartbeat holds secrets about stellar dynamics that continue to elude our complete grasp. 92. Cosmic rays' ultra-high energies. Cosmic rays are high-energy protons and atomic nuclei that travel through space at nearly the speed of light. While many originate from the sun or supernovae, some cosmic rays are detected with incredibly high energies, far exceeding what can be explained by known astrophysical accelerators within our galaxy. These ultra-high energy cosmic rays, UHECRs, are a profound mystery. What are their sources? They seem to originate from beyond our galaxy, but their extreme energies make them susceptible to the GZK cutoff, which predicts that they should lose energy over vast cosmic distances. This suggests they must originate from relatively nearby, yet no obvious powerful sources have been identified. Are they produced by exotic phenomenon like active galactic nuclei, gamma-ray bursts, or even the decay of super-heavy dark matter particles? The origin of UHECRs points to extreme astrophysical processes that we are only just beginning to comprehend, challenging our understanding of the universe's most powerful accelerators. 93. Lightning initiation physics. Lightning is one of nature's most spectacular and powerful displays, a massive electrical discharge that can span miles. Yet, despite centuries of study, the precise physics of how lightning initiates within a thundercloud remains a significant mystery. We know that ice particles and supercooled water droplets collide, separating charges within the cloud, leading to a buildup of positive and negative regions. But the electric fields generated by these separated charges are generally not strong enough to overcome the insulating properties of air and trigger the initial leader discharge. This discrepancy is known as the lightning initiation problem. What is the missing ingredient?
Are there exotic processes like cosmic rays, runaway electrons, or small pockets of highly conductive plasma that provide the initial spark? The exact mechanism that transforms a charged cloud into a catastrophic electrical discharge is a complex puzzle involving extreme atmospheric conditions and particle physics. 96. Gravity quantum unification. One of the holy grails of modern physics is the unification of gravity with quantum mechanics. Our two most successful theories, general relativity, which describes gravity and the large-scale universe, and quantum mechanics, which describes forces in terms of particle exchanges, example, photons for electromagnetism, are fundamentally incompatible. We don't have a consistent theory of quantum gravity. This means we cannot accurately describe phenomena where both extreme gravity and quantum effects are significant, such as the Big Bang or the interior of black holes. Theories like string theory and loop quantum gravity attempt to bridge this gap, but none have been experimentally verified. The inability to unify gravity with the quantum realm represents a profound incompleteness in our understanding of the fundamental laws governing the universe. 97. Consciousness and quantum links. Some highly speculative yet intriguing theories propose a link between consciousness and quantum mechanics. Could the non-local, probabilistic, and observer-dependent nature of quantum reality play a role in the emergence of consciousness? Is the brain, particularly at the microtubule level within neurons, somehow harnessing quantum phenomena to generate our subjective experience? The orchestrated objective reduction, ORC-OR theory, by Roger Penrose and Stuart Hameroff is a prominent example suggesting that consciousness arises from quantum computations within microtubules. While these ideas are highly controversial and lack strong empirical evidence, they represent an attempt to address the hard problem of consciousness by looking beyond classical neuroscience. The potential, however remote, for quantum mechanics to explain the mystery of consciousness remains a fascinating, albeit unproven, frontier at the intersection of physics and biology.
96. Animal consciousness levels. While we struggle to define and understand human consciousness, the question of consciousness in animals is even more complex and ethically charged. Do animals experience subjective feelings, thoughts, and a sense of self? And if so, to what degree? We observe complex behaviors, problem-solving, and emotional responses in many species, from primates and dolphins to birds and even octopuses. But how do we scientifically measure or infer consciousness in creatures whose brains are vastly different from our own? Where do we draw the line? Is a dog conscious? A fish? An insect? The absence of a universal definition of consciousness, coupled with the inability to directly access an animal's inner world, makes determining their levels of consciousness a profound scientific and ethical challenge. It forces us to reconsider our relationship with the natural world and the very definition of sentience. 97. Split brain mysteries. Patients who have undergone a corpus callotomy, a surgical procedure that severs the corpus callosum, the main communication pathway between the two hemispheres of the brain, are known as split brain patients. Studying these individuals has revealed astonishing insights into brain lateralization, yet also profound mysteries about consciousness and the unity of self. For instance, the left hand, controlled by the right brain, might perform actions seemingly independent of the right hand, controlled by the left brain. Or the patient might verbally report seeing one object while their left hand correctly points to another. Does a split brain patient have two independent consciousnesses, two separate selves, coexisting within one skull? Or is there a single fragmented consciousness? The split brain phenomenon challenges our intuitive sense of a unified self and raises deep questions about the modularity of the mind and the neurological basis of subjective experience. 98. Why music affects emotions. Music is a universal human phenomenon, capable of evoking powerful emotions, joy, sadness, excitement, nostalgia, across cultures and generations.
Yet the precise neurological and evolutionary reasons why music has such a profound and direct impact on our emotional state remain largely unexplained. How do patterns of sound, rhythm, and harmony trigger such visceral and complex feelings? Is it because music taps into ancient brain circuits related to movement, social bonding, or reward? Does it mimic the prosody of human speech or the rhythms of our bodies? While we can identify brain regions activated by music, e.g. the amygdala for emotion, the nucleus accumbens for reward, the specific mechanisms by which abstract auditory patterns translate into subjective emotional experiences are still a mystery. The emotional power of music is a testament to the intricate and beautiful workings of the human brain, a language that transcends words. 99. Origins of creativity. Creativity, the ability to generate novel and valuable ideas, solutions, or artistic expressions, is a uniquely human trait and a cornerstone of our progress. But where does it come from? What are the cognitive and neurological processes that underlie flashes of insight, imaginative leaps, and the synthesis of disparate concepts into something new? Is it a function of specific brain networks, an interplay between divergent and convergent thinking, or a byproduct of certain personality traits? While we can study its correlates and observe its manifestations, the fundamental origin of creativity, the spark that ignites innovation and artistic genius, remains elusive. Is it a purely rational process, or does it involve subconscious thought, intuition, or even a touch of madness? The wellspring of creativity, a defining aspect of our humanity, is a profound and beautiful mystery, a testament to the mind's boundless capacity for invention. 100. Why the universe is comprehensible at all. And finally, perhaps the most profound mystery of all, why is the universe comprehensible at all? We, as sentient beings, possess the capacity to observe, analyze, and formulate mathematical laws that accurately describe the workings of the cosmos, from the smallest subatomic particles to the largest galaxies. Why should the universe obey elegant, discoverable rules that our minds can grasp? As Einstein famously wondered, the most incomprehensible thing about the universe is that it is comprehensible. Is it a cosmic coincidence? An indication that our minds are somehow intrinsically tuned to the universe's structure? Or is it a consequence of the anthropic principle, where we simply wouldn't be here to observe it if it weren't comprehensible? This isn't just a scientific question, but a philosophical one, touching on the very nature of existence, knowledge, and our place within the vast, awe-inspiring tapestry of reality. And there you have it, 100 things that, despite our incredible scientific progress, continue to baffle, intrigue, and humble us. From the inner workings of our own minds to the farthest reaches of space, these mysteries remind us that the journey of discovery is far from over. Science, at its heart, is not just about finding answers, but about asking ever deeper questions. And in those questions lies the endless wonder of the unknown. Thank you for joining us on this journey.